Hi there. I'm Atindriyo Sanyal. I'm one of the founders of Galileo. And Galileo is a machine learning company, and we help data scientists curate high quality data sets for ML models by removing errors and various other issues that plague ML data today. And before this, I was leading various machine learning engineering efforts at Uber and Apple. And on Uber, I was part of the Michelangelo team, was one of the co-architects of the world's first feature store, and spent many years building feature stores before they became industry standard, and pretty much spent over 10 years of my career building some of the largest machine learning platforms in the world. And today, rather than going deep into a particular data-centric technique or an MLOps technology, I want to talk about some guiding principles that frames the building of a platform, which helps build high-quality models through high-quality data sets. Now, the goal of any person who's practicing ML in the industry today is very simple. It's essentially to produce high-quality models and do it fast. But the reality is that each ML project takes many months to go from identifying the problem and the use case all the way to deploying the model in production. And in fact, ML teams dedicate themselves to just deploying one model in an entire quarter. And this is the sad reality, despite various advancements we've made in model frameworks, which allow us to deploy models in 3 lines of code, and so many machine learning platforms that allow us to do click button training and deployment, and a slew of auto ML tools which are out there to police and govern our models in its journey along the workflow. And the reason for this is that high quality models depend on one very key thing. It is high quality data. And quality ML data is the largest impediment to seamless ML adoption across the enterprise. And this is literally the reality is that the difference between productionizing one model a quarter and the pipe dream of productionizing models on a daily or even an hourly basis is high quality data. Now here I've drawn a 30,000 foot view of an ML workflow. Now you have training data on the left, which gets fit to a model, which creates a trained model, and then you deploy the model to production, which generates predictions. Now, across the workflow, there's 3 important questions which any ML practitioner asks. Now, the first question is around the pre-training phase, where you ask how you choose what data to train and what data to label. And then once you have a labeled data set, how do you inspect and remove unneeded or noisy data from it? Then in the post-training phase, the question revolves around investigating the areas of weakness in your model and then fixing the data that the model performs poorly on, that brings your model performance down. And finally, the third important question to close the loop revolves around when you deploy your model, there's all kinds of shifts and variations in the traffic which occur. There's semantic drift, which happens where new clusters of data hit the model. There's concept drift, which happens in the long term with trends of changes. And the model gets outdated and it starts performing poorly. So the question is, how do we precisely measure these shifts and precisely measure how these shifts affect your model performance, and then accordingly choose the next cohort of data you want to train your models with so that your models remain updated continuously? So the first step towards answering these 3 questions is to identify the issues which are plaguing the modern day ML workflow. So to dive a bit deeper, here's the 5 steps of a standard ML workflow. Yeah, the first 2 phases revolve around identifying the use case and the problem and selecting the data that you want to send for labeling. And there's a sufficient slew of issues in this phase, which we like to categorize as data curation issues. Now, in this phase, the goal is to construct an ideal data set for training and evaluating your model. And most real-world data sets are plagued with issues around labeling errors, class imbalance, there's noisy data, as well as redundant features, where there's 2 or more features which contribute the same amount of knowledge to the label and to the model. And in my experience, I've cherry-picked certain models from production where you can essentially removing 80+% of the features achieves the same model performance. The next phase is part of the training phase where you do custom feature engineering to fit the data to the model. And over the years, the amount of model tuning code has reduced to a minimum because of advancements in hyperparameter tuning techniques, etc. And the amount of code that you write for doing the custom feature engineering in the pre-fit phase of your model occupies the most code real estate. And in this phase, the issues relate to essentially identifying the low-performing regions in your data, the data that pulls your model down. And these include, but are not restricted to, labeling errors, garbage, noisy data, biases in the data, as well as boundary samples, which are close to your decision boundaries, and they confuse the model. So the goal is to identify these and take action to fix the data set in a minimal number of steps. And then once the model is deployed and it meets the real world, there's the shifts in the traffic patterns. I categorize these as model freshness issues. And some of the key observations in my many years of building these kind of platforms has been that oftentimes there's very interesting correlations that you can find between some of the model metrics as well as some system metrics, for example, latency. As an example, there's very interesting correlations you would find when you look at high latency predictions and compare them to low latency predictions. Now, this brings me to the first principle to curating high quality ML datasets, and that is understanding your data is absolutely critical. Before we stitch together a data frame of features and labels, that we want to fit to the model, it's very important to understand, how your data is sort of distributed. And from an unstructured data perspective, it essentially means, getting a good sense of the semantic coverage of the data, what key semantic topics are covered in your data set, and how much of those are outliers and how much of noise exists in the data, and essentially how much data is semantically confusing to the model as well, because that data will bring your model down. Now, there's a lot that you can leverage with embeddings, which are vector representations of data, which can be reduced to a two-dimensional space to visualize them. And there's different techniques to calibrate these embeddings, ranging from simplistic techniques for text data, including TF-IDF and word2vec, but there's more advanced methods now where you can use pre-trained models to generate these embeddings. And on top of these embeddings, you apply clustering algorithms such as HDB scan or UMAP, and this really helps generate a keen understanding of the data that you're working with. Now, here's a glimpse of a workflow that I will demo later, where we are identifying certain clusters of your data, including erroneous clusters, zeroing in on them, and then removing them from the data set. Essentially, one term that I have used in my many years of building these machine learning platforms is that of a soft outage. And a soft outage is essentially an error which is generated because of biases and latent issues in your data. And these soft outages, they compound over time. They're very unlikely to be caught easily because they're so latent in the data itself. And once they get baked into your model after your training and evaluation, they become so nuanced and invisible to even software systems to detect, let alone the bare eye. And the outcome of these soft outages is bad predictions. And bad predictions bring down your downstream consumer systems, and eventually they affect your business. So it's critical to identify these kind of issues early on in the game so that they don't compound downstream in your workflows. The second principle is that with data, less is always more. There needs to be a focus on quality over quantity. And in the last slide, I spoke about soft outages. One of the issues or reasons for soft outages is also too much data. Because the problem with large quantities of data is that the more the data, the more the likelihood of errors and biases in the data, the more your labeling costs, and of course, the more the proclivity to having a large number of classes, which would lead to class confusion. With unstructured data, for example, it's good to focus on semantic representation and optimal coverage. And in practice, we've seen good results where you leverage the power of pre-trained embeddings to get a general understanding of your data, but you augment that in an active learning kind of an environment with your fine-tuned embeddings to get a more contextual representation of your use case. And using the active learning technique, you can essentially systematically augment your data set by cherry picking, particular sort of kinds of data that you need from different partitions of your data set. So to give a more practical example, say you have a data set for a single day of data. You can get similar examples in bulk from different partitions of that data, which can be from different days. And that's how you systematically kind of construct a minimal but high value data set for your model. Now, the third principle I feel is the Hallmark Principle for any robust ML platform. And that is the ability to evaluate a model on a hybrid set of metrics. There's, of course, the North Star metrics like accuracy and F1 and RMSE, which are pretty critical to measure and monitor for any ML practitioner. But the health of a model is determined by metrics which go much beyond the accuracy. There are some key metrics to monitor would essentially depend on which phase of the ML workflow you're in. And often these metrics are metrics which we measure for traditional software systems. As an example, there's prediction latency, which is essentially the end-to-end time for a model to deliver a prediction. And correlating that with accuracy or feature importance leads to very, very interesting insights for your model. So the lesson here is that you continuously evaluate on a hybrid set of metrics. To do this at Galileo, we've built the ability to measure these using what we call building blocks. And these building blocks can be applied to a model at any phase of the life cycle of the model. And I'll come back to this in a minute. But to jump into the fourth principle for building high quality models using high quality data is to understand your model's limitations. Now, a model is essentially like any other software artifact, just like you achieve a balanced sort of delivery of a software artifact like an API or a microservice by doing tuning of different parameters to achieve that optimal performance. The same holds true for a model. For example, there's mutations in your machine learning data that can improve the accuracy of in the model for a slice of data, but then regress the accuracy of another slice. So it's very important to understand and have a preconceived idea about where your model may or may not fare well so that you can set up your monitoring system accordingly. Now, the fifth and final principle to building high quality models revolves around the most important thing, which is actionability. Now, more often than not, bad data causes prediction issues and bad models. And it's not enough to just have a system which monitors and observes, key feature or model, prediction metrics. But to be able to pinpoint to the segment of data that led to the particular issue and suggest the action that's to be taken upon it, that's the hallmark of a good monitoring system. And with Galileo, we've built out these building blocks, which play a very key role in being able to systematically pin down the areas of your data which are erroneous. And through the Galileo SDK, you can do a lot of very interesting things such as creating predicates and conditions using code to be able to define the actions that you want to take upon the erroneous segments of your code once they're detected. This I feel is a key next step to every next generation ML platform, not just to be able to provide the ability to move a model from inception to deployment, but to continuously monitor the quality of the model, detect these key issues, and correct them automatically. And this is how you build and bake in actionability into a platform. Now, finally, before I sort of jump into the demo, I want to highlight the fact that the Galileo is being used in multiple enterprises of various sizes, and some of the outcomes and improvements that we've seen by adopting some of these principles in Galileo have been double-digit model performance improvements, during your training and evaluation. Close to 40% new errors have been detected in a matter of minutes. And in general, model productionization has gone from many, many days to a couple of hours. and not only because of quick detection of issues in your data, but also streamlining cross-team collaboration across labelers and modelers and product managers as well as leadership. Now, getting into the fun part, the demo. So just to set some context about the demo, the use case that I'm about to show you is a multi-class intent classification data set use case, where the input is a user utterance and the label is an intent that's assigned to the utterance. And the scenario here is that I'm an ML practitioner and I add a few lines of Galileo code to my model. I train my model just like I would without Galileo. And at the end of the training run, I get a link to the Galileo console. And I'm going to jump to the demo now. So once you're done with your training run, it leads you to this console, which, so just to give you a quick walkthrough of this Galileo console here, on the left-hand side, you have your experiments and your runs, and including the ability to compare runs within your experiments. In the middle here is the data bench, which a user essentially leverages to do error discovery and investigation. And on the right-hand side is a dynamically changing insights pane, which auto-updates as you do filters and other operations in your data bench. And this has all the key metrics that any ML practitioner cares about, including Galileo's own metrics, such as depth distribution and top misclassified pairs, which I will get into in a second. So the goal here is to identify key errors in your data set and fix them for your next training run. And let me walk you through the data set here. So in the data set view, we show you the samples, the ground truth, the predicted label, as well as a homegrown statistical metric, which we call depth or data error potential. And that is essentially a per sample metric, which measures how difficult it was for the model to train on that sample. And the way we measure depth is by observing the training dynamics across epochs for every single sample. So high depth samples are typically samples which are mislabeled, they're noisy, there's garbage, and they typically are samples which confuse the model. And throughout the platform, we always sort our data sets by depth so that you see the low performing and the erroneous samples right up top. At the top here, we also provide certain single click cohorts or interesting cohorts of data for you to investigate. For example, the first cohort is hard for the model, which will give you the set of samples which were very difficult for the model to train on. So if you click here, there's internal calibrations which Galileo does to compute the smart threshold beyond which we categorize each sample as hard. And you can see that a lot of these hard samples, there's so many errors in them. For example, the first few samples are clearly mislabeled. Play a soundtrack is labeled as get weather. Add this artist is labeled as get weather. What movies are close by labeled as great book. And if you go down this list, you'll see there's a lot of samples which have ground truth errors in them. One thing that Galileo also does is that it auto-instruments the embeddings from the model as it trains. And we give you a nice visual representation of the embeddings once your training run is done. So in this case, you can see the embeddings are colored by your ground truth, but you can also color by different metrics, such as your data error potential. Over here, this gives you like a nice bird's eye view of what the model was able to train easily and did well on versus where it struggled. So clearly there's three islands of data here which the model struggled with. So if I hover over them and I investigate them, it's very evident why the model was struggling here. These are all empty samples. And if I go up top here, these are all garbage samples. So the model was having a very hard time with these samples. And so what I can do is that in the platform itself, if I draw a lasso around this particular cohort, I can investigate on the right-hand side and see that it consists of about 1.5% of my overall data set. Almost all of it is very hard for the model. Uh, the F1 for this particular cohort is 57 percent points below the overall F1, and clearly you can see that there's a skew in the number of in the samples labeled as none in this cohort. So in a matter of seconds, you get some very interesting insights here about this data. But the question is, now you want to take an action on this data. So if I go back to my data set view, it dynamically updates to just show me these particular samples, which I've selected. And in the console itself, I can take one of these actions up top here. In this case, I have decided to remove these empty samples because I don't want them in my training data set. So I just hit remove. I add a little note, samples not needed, and I hit the remove button, and this gets added to what we call an edits card here on the right. And I'll get to the edits card in a minute. But let me take an action on the other cohort of garbage data, which I had just discovered. If I zoom out here, this island here is that of garbage data. If I hover over it, I see that it's 71 percent points below my overall F1. So it's clearly a very hard sample. But in this case, I don't want to remove these samples. I want them to remain in my data set because they would robustify the training of the model. But I do want to make sure that the labels are correct. And if I show you the ground truth and the prediction here, you will see that there's a lot of diversity and confusion here around these garbage samples. So one action I want to take is label all of them to the none label, which is what I want to categorize my garbage samples as. So if I just hit change label, I have the option to either label it to what my model said, if you trust the model enough, but I can also manually label it to none, which I want to do in this case. So if I hit change, it again gets added to my edits card. So going into the edits card, as you would expect, the edits card is a card which sort of has your the roster of mutations that you've done as on your data set as you've discovered different errors, and it shows you the entire lists. For example, here I removed a bunch of samples, I relabeled a bunch of samples, and I can take a quick action by simply hitting the export button. And here I have the option to apply all these edits on top of my base data frame and either download the data in a format of my choice, which is compatible with my machine learning framework, or I can directly send it to either S3 or Delta Lake, and we have bespoke integrations with certain commonly used ML data stores. But one of my favorite actions that you can take is directly get this data frame in code. And here, in one line of code, I can simply copy this, go back to my model development environment, whether it's a notebook or any Python script, and I can just paste this code and run it, and I would get my mutated data frame where all the edits that I've made would be applied on top. So this shows you how you can sort of discover and fix errors very quickly. One other thing which I want to highlight here is if you look on the insights pane here, one thing you notice is that there's a clear class imbalance between some of the other classes and book restaurant, which clearly lacks a robust number of samples. So in the platform itself, you can curate your data set by augmenting high quality samples for the book restaurant class. And you can do it by simply clicking on this bar, which would show you all the samples which were annotated as book restaurant. But I want to look at only the high quality ones, which the model was able to train on easily. So I hit easy for the model. I bulk select all these samples, and I get similar samples from a different run. So this is where Galileo's power really shines through, is that you can do like cross data set similarity cherry picking. In this case, I have done an inference run on my unlabeled data under this project, and which has shown up here, and which has data for which is semantically similar to utterances which revolve around restaurant booking. So if I just select that run and I do find similar, it takes me to my inference console, which is a whole world of its own. But in this case, I want to essentially select all these samples which Galileo has given me and either add them to a label cart where I can essentially trust the model and just label them as book restaurant, or we have integrations with labeling tools where you can directly send this cohort of unlabeled data to your labelers in the click of a button, and you get back new samples for book restaurant, which would augment your training data set. So hopefully this gives you a good idea about how to use Galileo for error discovery investigation, as well as sampling and dataset curation. There's a lot more in the console, which we haven't covered in the demo. But coming back to the presentation here, there's one good news that I want to share, that Galileo is available today for free. So you can essentially just go to rungalileo.io, which is our website, and you can sign up using your Google account. And when you enter the console, you'll see a lot of goodies, including example runs, which we've done on public data sets, as well as example notebooks, where using different frameworks, which you can get access to right from the console. And you can start training your own models with Galileo today. So really encourage you to sign up and use Galileo on your ML data. Thank you very much.